There are buildings standing in Europe right now that should not be standing. Not because they're fragile, because they are extraordinarily ambitious structures built without a single tool we would recognize as necessary for the task. No steel, no concrete, no cranes in the modern sense, no structural calculation software, no engineering degree. And yet, Chartres has stood for 800 years, Notre-Dame for 850, Cologne Cathedral for over 600, and it is still not entirely finished. These buildings did not survive by luck. They survived because someone understood structural engineering at a level that we are still, in some respects, reverse engineering today. And that someone left no name. We do not know who designed Chartres Cathedral. We do not know who calculated the flying buttresses. We do not know who solved the acoustic problem of the nave. We have their work. We do not have their names, their notes, their calculations, their failures. Everything we know about how they did this, we have inferred from the buildings themselves. To understand what these men achieved, we need to understand what they were working with: stone, timber, iron in limited quantities, rope, and knowledge that existed nowhere in written form. The stone for Chartres came from quarries at Buttress, 12 kilometers away. Moving it required ox carts, river barges, and a labor organization of extraordinary complexity. Historical records from the period describe local populations volunteering to haul stone, not as forced labor, but as an act of devotion. Communities pulling carts themselves because the building was theirs. This matters for understanding the engineering. The master builder was not operating in isolation. He was operating at the center of a social project that had the devotional energy of an entire region behind it. That energy funded experiments. It funded rebuilding after failures. It funded the patience to get it right across decades and generations. The first question is the obvious one. How do you build a stone vault 100 feet in the air without steel reinforcement? The answer involves a system of distributed forces that took medieval builders generations to understand and refine. A stone vault pushes outward as well as downward. If the walls cannot resist that lateral thrust, they crack and the vault collapses. The flying buttress is the solution, an external arch that catches the lateral thrust before it reaches the wall, redirects it downward, and deposits it into a massive pier in the ground. What makes this invention remarkable is what it enabled. By moving the structural work outside the building, the builders freed the interior walls from their load-bearing function, and a wall that does not carry load can be made of glass. This was not a decorative decision, it was an engineering decision that had a theological consequence, or a theological decision that had an engineering solution. It is impossible to separate them. Light was theology. The Abbot Suger of Saint Denis, one of the earliest patrons of Gothic architecture, wrote explicitly about Lux Nova, new light, as a spiritual condition that architecture could produce. Suger wanted a building where light itself was the material of the sacred. The engineers gave him one, but to give him one, they had to solve problems that had never been solved before. This solution was not obvious. It was arrived at through a process that involved building, failure, partial collapse, rebuilding, and refinement across generations. Some of those partial collapses are documented. Beauvais Cathedral collapsed twice. The choir vault fell in 1284. Part of the transept collapsed in 1573. Beauvais was rebuilt after each collapse, each time taller. It remains the tallest Gothic choir vault ever built. It has no nave. The builders ran out of money and ambition simultaneously. What Beauvais represents is not failure. It is the outer edge of what medieval structural engineering could achieve. the point where the ambition exceeded even their extraordinary competence. Now consider what this means. These builders were operating without structural theory in the modern sense. They had no equations. They had precedent, proportion, and accumulated craft knowledge. The proportional systems they used, based on geometric relationships rather than numerical calculation, produced structurally sound buildings because geometry, correctly applied, encodes physics. The primary geometric tool was the Vesica Piscis, the intersection of two circles of equal radius. From this single construction, the master builder could derive the proportions of the entire building without measuring a single dimension in feet or meters. The result is a building whose proportions are internally consistent, from the width of a stone column to the height of the central tower, because everything was derived from the same geometric seed. They knew this worked because it had worked before, and when it did not work, they rebuilt. This is empirical engineering. It is slower than theoretical engineering. It is more expensive, and it produces buildings that have stood for 8 centuries because the margin of error was resolved in stone before the scaffolding came down. The men who cut this stone were not laborers in the modern sense. They were craftsmen with decades of training, organized in a hierarchy of skill that determined what each man was permitted to cut. An apprentice cut rough blocks, a journeyman cut moldings, a master cutter worked on the complex geometries of capitals, keystones, and tracery, and above all of them, the master builder, who cut nothing himself but held the geometry of everything in his mind. The master builder was the most important person at the construction site and among the least documented. We know the names of bishops who commissioned cathedrals. We rarely know the names of the men who built them. There are exceptions. We know the name of Villars de Honnaucourt, a 13th century master builder who left a sketchbook, 33 pages of drawings covering geometry, architecture, machines, and human figures. The sketchbook is extraordinary, and it raises more questions than it answers, because what Villars draws is not explained. The geometric operations are shown without commentary. They were meant to be understood by someone who already knew the context. This sketchbook was not a teaching manual, it was a personal reference, notes for a mind already full of knowledge that needed only to be reminded, not instructed. Now let us consider the acoustic problem, because the engineering of these buildings was not only structural. A Gothic cathedral is a purpose-built acoustic instrument. The reverberation times, the duration of sound after its source stops, in these buildings range from 4 to 10 seconds. Modern concert halls aim for 2 seconds of reverberation. These buildings were built with 4 to 10 because Gregorian chant, the music they were designed for, requires a long reverberation to achieve its specific sonic effect. These builders achieved this not by accident, but by choice of material, geometry of surface, and proportion of space. Thick stone walls absorb low frequencies differently than they absorb high frequencies. They knew this from experience, not from acoustic physics. They knew what it sounded like, and they reproduced it. Some cathedrals have acoustic anomalies that are clearly intentional, specific points in the nave where a whisper can be heard clearly at the opposite end of the building. These are not accidental. They result from precise curvature of vaulted surfaces directing sound waves along specific paths. Researchers at the Technical University of Denmark have measured and modeled the acoustics of multiple Gothic cathedrals. Their conclusion is consistent. These buildings are not acoustically accidental. They were tuned. Tuned without microphones, without oscilloscopes, without the mathematics of wave physics. Tuned by ear across decades by people who knew what the building needed to sound like because they had heard it sound right before. Who calculated these curves? We do not know. The knowledge lived in the hands of the master builder, transmitted through practice, and died with him. This is perhaps the most significant thing about the anonymous engineers of the medieval cathedrals. The knowledge was embodied, not written. It lived in the gestures of the hand, in the eye trained to read proportion, in the accumulated judgment of a career spent cutting stone. When a master builder died, the knowledge died with him, unless he had passed it on through years of direct apprenticeship. When a cathedral project lost its master builder mid-construction, the results were sometimes catastrophic. William of Sense, the master builder of the choir of Canterbury Cathedral, fell from the scaffolding in 1778. He was carried back to France. The project continued under a different builder, William the Englishman, who finished the work but made different choices. The seam between the two builders is visible in the stone today. That seam is one of the few places in a medieval cathedral where you can see an individual human event. A man fell. The building changed. The stone remembers. The lodge system, the Mason's Lodge attached to each cathedral, was the institution that preserved and transmitted what could be preserved and transmitted. The lodge was a school, a workshop, and an archive simultaneously. Geometric templates were stored there, full-scale wooden or stone patterns from which complex moldings could be reproduced exactly across decades of construction. These templates allowed a window molding begun in 1200 to be continued identically in 1240 by men who had never seen the original cutting. The template carried the knowledge across time. Some of this knowledge eventually became the foundation of what we now call Freemasonry. The geometric symbolism, the hierarchical structure of apprentice, journeyman, master, these survived the cathedrals. The knowledge that built the cathedrals did not die entirely. It transformed, encoded itself in ritual and symbol, and waited. But what was lost is significant. The specific structural intuitions, the acoustic judgment, the proportional systems, these cannot be fully recovered from the symbols alone. Modern engineers have studied these buildings with instruments their builders could not have imagined: laser scanning, finite element analysis, acoustic modeling software. What they have found consistently surprises them. The ribbed vaulting of Gothic cathedrals distributes loads along paths that finite element analysis confirms are nearly optimal, not approximately optimal, nearly optimal. This means the builders found, through empirical practice and geometric intuition, solutions that our mathematical methods confirm are close to the theoretical best possible answer, without knowing why it was optimal, without being able to express it in those terms. They knew it worked, and they were right. The stained glass adds another dimension to the engineering problem, because glass changes the structural behavior of the wall. A wall of glass is weaker than a wall of stone. The medieval builders knew this. Their response was to make the stone skeleton so efficient that the glass panels became essentially non-structural, infill between load-bearing ribs. This required the stone skeleton to carry all lateral wind loads as well as the dead load of the vault above. The flying buttresses, again, are the solution. And the glass itself is engineering. Medieval glass is not uniform in thickness. It is thicker at the bottom of each panel than at the top of each panel. The glassmakers of the medieval period understood color chemistry in ways that modern analysis continues to unpack. The deep red of 12th century glass at Chartres has never been perfectly replicated. The secret is in the gold content. Microscopically thin layers of gold suspended in the glass matrix produce a red that modern glassmakers, using modern processes, have not been able to reproduce to the same depth and consistency. This was partly a consequence of the manufacturing process, but the builders used the particular qualities of their glass deliberately, understanding that glass of varying thickness and density produces a richer, more complex quality of light. The quality of light in a Gothic cathedral is not accidental. It is a designed experience, the result of choices about glass color, thickness, window orientation, and the geometry of the space that receives the light. These builders understood light the way a composer understands sound. They were engineering a perceptual experience. And they did all of this while simultaneously managing construction projects of extraordinary complexity. Hundreds of workers, dozens of specialized crafts, supply chains for stone from quarries sometimes hundreds of miles away, all coordinated over timescales of decades. The logistics alone represent a separate engineering achievement. The Great Wheel Crane, a human-powered wooden wheel 12 feet in diameter, within which workers walked like hamsters to drive a rope and pulley system, could lift stones weighing several tons to the height of the clerestory. These cranes were left in place inside the roof space after construction. Some survive. In the roof of Salisbury Cathedral, a medieval crane has sat unused for 600 years. The logistics alone would challenge a modern construction firm. These men did it with hand signals, apprenticeship relationships, and the authority of the master builder's geometric drawings. Some of these projects ran for 200 years. The master builder who began the work would never see it finished. His successor's successor might not see it finished. They were building for a future they would not inhabit, for grandchildren who were not yet born, for a community across time. This temporal ambition is unique in the history of construction. It changes everything about how decisions are made. When you will not live to see the outcome of your structural choices, you default to permanence over economy. They were not building for clients in the modern sense. They were not building for personal recognition. They were building for God, which meant they were building for permanence. And permanence changes your engineering decisions in every dimension. You over-engineer because you are not building for 20 years or 50, you were building for always. The foundations of Chartres go down 6 meters, the walls at the base are 4 meters thick. The building weighs hundreds of thousands of tons and distributes that weight through a system of foundations calculated empirically by building smaller things first, watching how they settled, and scaling up. This approach, build, observe, adjust, scale, is the engineering method of a tradition that cannot afford to be wrong, because wrong means collapse, and collapse means lives and decades of work destroyed. The cathedrals that stand today are the ones that got it right. The ones that got it wrong are ruins, or have been so extensively rebuilt that the original engineering ambition has been moderated. The survivors are a selection of successes. We're still learning from this. The engineering departments of universities still send students to Chartres, to Amiens, to Reims, not to admire, but to measure and to think. What they find each time is the same thing, a building that knew more than its builders could explain. There is a question that sits beneath all of this that is rarely asked directly. What does it mean that our so sophisticated analytical tools confirm the optimality of solutions reached without theory? It means that practice, conducted with sufficient care and over sufficient time, can arrive at truth. Not approximate truth, not good enough truth, the actual answer. This is a challenge to how we think about knowledge. We tend to assume that explicit knowledge, written, theoretical, mathematical, is superior to embodied knowledge. The cathedrals suggest otherwise. The anonymous engineers of the medieval cathedrals left no papers, no calculations, no names on the buildings they made. They left the buildings, and the buildings are still teaching.
Thanks for watching. Don't forget to subscribe and turn on notifications so you never miss a new video. See you in the next one.